Hello everyone. In this talk, I will present on the absence of ultimate regime in turbulent convection. We'll discuss about ultimate regime and its absence. And this work is done in collaboration with my collaborators here. And we use these computing resources. This work is published in PNS 2025, and you can also refer to my book for reference. All right, so I will describe what the problem is. For a small temperature difference between two plates, there's a fluid in between. When temperature difference is small between the plates, the heat goes up by conduction, molecular diffusion, right? And the fixed law says that heat flux is proportional to delta T. H is the heat flux. However, when the temperature difference becomes large, then um, the heat transport also gets contribution from the velocity field, the fluid velocity field, hydrodynamic velocity. And for large delta T, what dominates is the convective part. As a result, the heat transport is enhanced and is delta T to the power 1.3. We use in literature a Nusselt number, which is a non-dimensional number, um, signifying the total heat flux divided by the conductive heat flux. So ratio of this versus this naturally is delta T to the power 0.3. And we define a new parameter called Rayleigh number a bit later, which is proportional to delta T. So Nusselt number goes as Rayleigh to the power 0.3. Observed in experiments and simulations. Now, if you look at some of the models, one popular model is that heat transport goes as delta T to the power 1.5. Okay? So this is called ultimate regime. For very high temperature difference, Crichton argued that heat flux is this, and that gives you exponent of half. Nusselt goes as Rayleigh half. Okay, so the competition between this half and 0.3. Okay, and I will show that in this presentation, the real exponent is near 0.3. Now, why so? Is a crux of the paper, which I'm going to tell you. The positive heat flux, which is hot plume is going down or cold going coming down. Sorry, hot going up and cold coming down. That's a natural mindset we got for convection. However, uh, I will show in this paper, in this presentation, that hot can also go down. Hot fluid can go down. We find that the red fluid, which is hot, is coming down. And the difference is leads to 0.3. So there is a negative flux compensation. So we get the net heat flux is 0.3 because of the negative heat fluxes. The setup which we're going to employ is for this presentation, I'm going to explain is Rayleigh-Bénard convection. Here there's a velocity field and temperature field, and the fluid is confined between two plates. The parameter which I mentioned before is called Rayleigh number, which is the ratio of the buoyancy, which is on top, and the bottom is viscous term, and this ratio is called Rayleigh number. And we deal with Rayleigh number 10 power 13, 10 power 14, and like that, very large Rayleigh numbers. And for these Rayleigh numbers, we want to see the scaling, which is 0.3 or half. Nusselt number I already have defined before. Now we use Dhara, our finite difference code for this work. It's written in Python, it's GPU enabled. In fact, a lot of our runs were on GPU, which made it faster. Now let's relook at the three theories. First is ultimate regime theory, which is by Crichton. Nusselt goes Rayleigh half. It's connected to the boundary layer, okay? Boundary layer transition. Some experiments claim that we are going towards that thing, but nobody's reached half. But 0.35 exponent has been observed in some experiments. However, some other experiments only see 0.3 or 0.31. And this theory is called classical scaling. and it is based on Malthus, Priestley, and Spiegel's argument. Um, okay, I won't get into argument. I'll just say that is point 0.3. Now, third one is velocity temperature correlation. So we are non-dimensional velocity, non-dimensional temperature. I'm skipping one, okay? Plus one is there, but I'm skipping that. So these are convective transport. We rewrite this as RMS of UZ, RMS of T prime, and multiplied by the non-dimensional number. So this expression is same as that expression, apart from one. Now, this one goes as Rayleigh half, okay, dimensionally, nearly seen everywhere. Delta T goes as Rayleigh 0, it is independent of Rayleigh, but this object goes as minus 0.2. Now, this we published in 2012. We didn't really know why it is so, but now we know why it is so. It's because of negative heat fluxes. And together, half minus 0.2 gives you 0.3. So this is observed. Okay. So we are revisiting this theory, which was done around a decade back. Now, what are these negative and positive heat fluxes? This is an important slide. So without any temperature gradient, it's called scalar turbulence. So this homogeneous isotropic turbulence. If you have a positive hot plume, it can go up or down. There's no temperature gradient, so it can go up or down. So this is like ink; it can go up or down. Okay. However, when you apply a temperature gradient, but no walls, if there's no wall but apply temperature gradient, then the hot plume goes up. But it doesn't go down because it's being forced to go up. So positive heat flux wins over negative heat flux, and this gives you Rayleigh half. That is a periodic boundary condition. It has been shown that is half. However, when you apply plates, so this one has plates, means walls, as well as gradient, and then positive ones win over negative ones, but they are approximately similar magnitude. Okay, so you see the hot plume is going up, which is expected, but hot plume can also go down, and the large number of them are going down. This happens in RBC as well as compressible convection. Okay, now this is simulation which we did recently. So periodic box, you can see that there are a lot of positive heat fluxes. You see there are a lot of positive heat fluxes. Red is positive. Okay, red is positive here, but we have tiny amount of negative heat fluxes, pretty small. So positive ones are much bigger than negative ones, and we get Nusselt is Rayleigh half. However, for Rayleigh-Bénard convection and compressible convection, we get positive and negative in roughly uh, near amount of positive and negative heat fluxes. So you can see positive and negative are roughly same amount, a lot of positive and a lot of negative for both RBC and compressible convection. Now, this is a visual picture, but we can also look at the numbers. This is Nusselt for this is RBC, and this is RBC, and these are compressible convection, bottom ones, and 0.3, 0.3 roughly. But periodic is near 0.5, total Nusselt. However, we can break into positive and negative fluxes. So we non-dimensionalized it, okay? So the prefactor is square root Rayleigh, square root Prandtl, okay, prefactor. So we compute these quantities and plot them as function of Rayleigh in this plot, okay? Now there are too many curves here, but just focus on one of them, RBC. So positive ones are here, the solid line, which is the normalized ones is coming down. Is near zero, but is minus 0.07. This is the 0.07. The dash one is negative one. Okay, negative one also coming down, but the difference is shrinking with Rayleigh. You see, the difference is shrinking with difference between positive and negative. So the difference is going as minus 0.2, and now we plug that in this formula. So there's a prefactor Rayleigh half here, half minus 0.2, which gives you Rayleigh 0.3. Please recall that this 0.2 we had seen before for the normalized flux. So in fact, this quantity Fz, this difference is that normalized stuff we had seen in 2012 Physical Review E. So in summary, turbulent convection with walls exhibits both positive and negative heat fluxes, but the difference compensates from half to zero point 0.3. So uh, without walls, we get half, but with walls, because of the negative fluxes, we get zero point 0.3. So that's our conclusion. Thank you for your attention.